going to continue with more gas laws, and so I'll try to make this as quick as I can because we do have a bunch of gas laws to still get to. So the last ones we covered were Boyle's law, Charles's law, and Gay-Lussac's law. So in this case, just a refresher, the idea was that for Boyle's law, if one variable increased, the other one decreased. They were inversely proportional. For Charles's law, if one variable increased, the other one increased as well. For Gay-Lussac's, same thing. If one decreased, the other one decreased. These two are directly proportional, which means they change in the same direction by the same proportion, and Boyle's law is the only one that is inversely proportional, which means if one rises, the other one decreases, but it happens by the same factor. So in each of these cases, two variables were held constant. Remember, the variables that we have to play with are pressure, volume, temperature, and the number of moles. So in Boyle's law, temperature and the number of moles are held constant. In Charles's law, pressure and the number of moles remains constant. And in Gay-Lussac's law, volume and the number of moles remains constant. So the next law that we're going to introduce actually takes one more thing into consideration. What if instead of two variables being constant, what if only one was held constant? And that specific one that we're going to hold constant is the number of moles. That means we wouldn't be able to use Boyle's law to solve the problem because temperature would not be constant. We couldn't use Charles's law because pressure wouldn't be constant. We couldn't use Gay-Lussac's law because volume would not be constant. Except the thing is that there's a relationship between these three laws. They're all interconnected, they're all interrelated, and we can actually combine them. And we'll do so like this. This is it right here. We've combined all three gas laws together, and we will call this the combined gas law. It's very creative. So let's have a little wow moment for a second. Boyle's law. Now remember, in all of these laws, we know that the number of moles is constant. But for Boyle's law, what is held constant? Very good, temperature. Well, if temperature is the same on both sides, you can remove it. And look at that. You've got Boyle's law. If you consider Charles's law, what was held constant? Pressure. Well, if pressure is the same on both sides, we can cross it off. And look at that. V1 over T1 equals V2 over T2. That's Charles's law. Gay-Lussac's law, the thing that was held constant was volume. Well, that means we can cancel it out. We can reduce it from the equation. And P1 over T1 equals P2 over T2 is Gay-Lussac's law. So they're all embedded in this combined gas law. You can always use the combined gas law when you're solving any of these three problems, because if you were doing a Boyle's law problem and you use the combined gas law to solve it, since the temperature didn't change, you could either plug in the same number in both cases as you try and solve it, or recognize that and not include it. So the combined gas law allows you to not have to worry about the actual individual gas laws for each of those three. So let's go ahead and solve a combined gas law problem. Alright, so the volume of a gas-filled balloon is 30 liters at 40 degrees Celsius and 1.51 atmosphere. What volume will the balloon have at standard temperature and pressure? And in case you forgot, standard temperature and pressure are 0 degrees Celsius and 1 atmosphere. So let's go ahead and underline relevant information. So we know that the volume of a balloon is 30 liters. We know that our temperature initially is 40 degrees Celsius and that our pressure initially is 1.51 atmosphere. We want to find a new volume at standard temperature, which is 0 degrees Celsius, and standard pressure, which is 1 atmosphere. So remember, the combined gas law is P1V1 over T1 equals P2V2 over T2. Remember, the subscripts 1 represent before a change and the subscripts 2 represent after a change. So let's go ahead and write in our values. Our initial pressure is 1.51 atmosphere. Our final pressure is 1.00 atmosphere. For our volume, our initial volume is 30.0 liters, and we don't know what the final volume is. And for temperature, our initial temperature is 40 degrees Celsius, but you must remember that when we're doing gas laws, temperature must be recorded in Kelvin. So this needs to be converted to Kelvin by adding 273 to it, so we get 313 Kelvin. And our final temperature is 0 degrees Celsius, but it has to be in Kelvin. So when we convert that, 0 plus 273, I think, is 273 Kelvin. Now we can go ahead and plug in our values. Actually, no, let's simplify this. We want to solve for V2. I prefer to rearrange equations before we start plugging in numbers, and so we can do that by thinking like this. If we want to get V2 by itself, we want to isolate it, we can't because P2 is being multiplied by it. So in order to get rid of it, we're going to have to divide both sides by P2. That means on this side, P2 is going to be placed on the bottom. And then V2 is also being divided by T2. Well, if it's being divided by T2, we can get rid of it by multiplying both sides by T2, which is going to put T2 up on the denominator side. So when we rewrite this equation, we're going to get V2 is equal to P1 V1 T2 over T1 P2. So now let's go ahead and plug in the numbers. V2 is equal to those values right there. Right, so we just went ahead and plugged in for each of them. Let me just double check to make sure I place the correct ones. Sure, looks like I did. Alright, so you take out your calculator and you calculate it. Our final answer should have 3 sig figs, and it comes out to 39.5 liters. And that's how you solve a combined gases law problem. Anytime none of the 3 variables are constant, this gas law will come in handy. Or if it's a Boyle's law, Charles's law, or a Gay-Lussac's law problem, you can use this combined gas law to solve it as well. Because if any of these 3 variables are constant, you can just remove it from the equation. Let's move on to the next gas law. Avogadro's gas law. So it's similar to the previous 3. The only difference is the 2 variables that do change are volume and the number of moles. So your equation is V1 over N1 equals V2 over N2. So your variables that are held constant are temperature and pressure. You have a direct proportional relationship in this case as well. So what that means is if the number of moles increases, then the volume is going to increase. This is most similar to blowing into a balloon, right? So when you blow into a balloon, more particles are going into the balloon, so the volume of it increases. The pressure remains constant because even though you blow into the balloon and there's an initial increase of pressure inside the balloon, the pressure immediately expands until it reaches the same pressure as the atmosphere. So it restabilizes to maintain the same pressure. So yeah, that's probably the best example for Avogadro's gas law. So now let's work out a problem that you're probably not going to like. All right, so here it says, assume a 12.2 liter sample contains 0.5 moles of O2 at 1 atmosphere and 25 degrees Celsius. If all this O2 were converted to ozone at the same temperature and pressure, which means we don't need to care about temperature or pressure because it doesn't change, so it's not going to come out of the equation. What would the volume, what would be the volume of ozone? Okay, so first let's even understand what the question is asking. Since we're looking for a volume and we had an initial volume, that implies that the container of this substance is expandable, so we'll just say maybe some kind of balloon or expandable material of some kind. So since temperature and pressure are constant, we know that we can turn to Avogadro's gas law. So this should be pretty easy, right? So V1 equals N1 equals V2 N2. All right, so let's go ahead and write down what we know. So we know that our initial volume is 12.2 liters. And we know that the initial number of moles is 0.5 moles. And we know that we're looking for the V2 value, right, or the final volume. And it does not tell us the number of moles after. Like I said, you're not going to like this problem. So it tells us that in this problem, if all the O2 were converted to ozone, we have enough to solve this problem. Some of us just don't know it yet. We have to find N2 before we can find V2. So a little bit of stoichiometry here. We have a chemical reaction taking place. O2 is converting to O3. So if we have stoichiometry involved, or a chemical equation, we better make sure that it's balanced. So go ahead and balance it. Very good. 3, 2. Now it says if all the O2 were converted, you have 0.5 moles of O2. So if it all got converted to ozone, how many moles would that be? So after this reaction takes place, the number of moles is going to change. And if the number of moles changes, then the volume is going to change, because that's how Avogadro's law works. So let's do some stoichiometry. We have 0.5 moles of O2, and the relationship is for every 3 moles of O2, we make 2 moles of O3. So 0.5 times 2 is 1, divided by 3, we're going to get 0.3 moles of O3. And I know some of you don't like that, but unfortunately I gave you a problem with just one significant figure, so that 0.3333 has to be rounded to just 0.3. And now we know N2. N2 is 0.3 moles. So now we got to solve for V2. Real quick before we actually do it, notice how the number of moles or number of particles went down from 0.5 to 0.3. Well, if that decreases, and Avogadro's law, it represents a directly proportional relationship between volume and the number of moles, then we should expect volume to decrease as well by the same factor. So if we want to solve for V2, you've got V1 over N1 equals V2 over N2. We can isolate V2 by multiplying both sides by N2. And when we do that, V2 is equal to V1 times N2 divided by N1. Just like that. And our new volume comes out to 7.32 liters. And we'll go ahead and keep 3 significant figures. I know the math work should limit you to 1, but just because I feel like it, we'll leave it at 7.32 liters. All right, let's move on to another gas law. Okay, so we're looking at situations that involve pressure, volume, number of moles, and temperature. And we've looked at cases where pressure and volume, I'm sorry, not pressure and volume. We looked at cases where 2 variables are changing and 2 are held constant. We looked at a situation where 3 of the 4 variables are changing and 1 remains constant. So if you haven't figured out already, what happens if none of them remain constant? Is there a way to solve that? And yes, there is a way. So remember the gas laws. Boyle's law was P1 V1 equals P2 V2. Charles's law was V1 over T1 equals V2 over T2. Guy-Lussac's law was P1 over T1 equals P2 over T2. And we just did Avogadro's, so that was V1 over N1 equals V2 over N2. There is a way to solve a problem that involves these four variables where all of them change, and that happens by combining all four of them, because these four are all interconnected. So we're actually going to take these four equations and turn them into this. Here it is, the super duper mega combined gas law. So this is actually kind of crazy, but it's really nice because it really lets you figure out a new value when 3 out of the 4 variables are known and you're looking for the fourth one. Now, this kind of problem can be rather lengthy, and I actually intend to simplify it. So the main idea behind these gas laws is that one side of the gas law is actually equal to a constant. And after you make the changes, after a change has occurred, it also equals a constant. And it turns out it's that same constant. That's what allows both of them to be equal to each other. And in this gas law, there's actually a specific constant that it's equal to, and it's represented by the letter R. The value R is, the R is known as the universal gas constant, and it actually has a specific value. It is 0.0821 liters times atmosphere per mole Kelvin. And that should make sense because you've got liters times atmosphere per mole times Kelvin. Now it also has a different value depending on the units, but when the units are liters atmosphere per mole Kelvin, the value will always be 0.0821 because that is your universal gas constant. And I'm actually not going to have you solve problems using this relationship here. Instead, I'm going to have you use this relationship, PV over NT, and we're going to include that R. So we're basically just replacing the change into just the constant. I know that looks super gross, so we'll clean it up right now. PV over NT equals R. And we actually see it in a different way. It's actually written like this more commonly. PV equals nRT. This is just so we can avoid fractions. And also it's not called the super duper mega combined gas law, now that I think about it. It's actually just called the ideal gas law, because it's used to predict variables of gases, ideally. And goodness, we're going to open a door here. So it turns out that this ideal gas law is a model that we use to describe gases because the model is simple and it sort of ties in with the kinetic molecular theory. But these are ideal gases, ideal scenarios. It turns out in the lab that most gases don't behave ideally. That's because they're not ideal gases, they're what are called real gases. And some of you probably don't care about this real twist that I'm going to throw at you in a moment, but we say, according to the kinetic molecular theory, that gas particles travel in straight lines until they collide, right? And then we say that gas particles do not exhibit attractive or repulsive forces. So if they were traveling right past each other, there would not be any kind of influence. And we also say that these particles are so small, their volume is basically nothing. Well, that's ideal. That would be nice. Except that's not really what happens. It turns out that some particles, it turns out that real gases do exhibit attractive or repulsive forces, and that does affect pressure of gases. And it turns out that that particles do have volume, and that also affects pressure depending on the size of the particles. But that becomes a very, very complex problem, and that actually comes out of the ideal gas law. We actually replace we replace pressure and volume with some other equations, with some other expressions to kind of help better include some repulsions and attractions and consider the volume of particles. And it gets real intense and crazy, but you don't have to worry about that for now. So we're just going to stick to the very simple. Assume we're working with ideal gases unless told otherwise. And here in honors chemistry, that's really what we'll do. We'll see real gases in AP chemistry a little bit, but you won't lose a night's sleep over that. All right, so let's solve an ideal gas law problem. All right, so here it is. A 20-liter steel cylinder, a metal cylinder basically tells us that the volume is not going to change, is filled with nitrogen to a final pressure of 231 atmosphere at 35 degrees Celsius. How many moles does the cylinder contain? So let's say you had to solve some problems, but I didn't tell you what gas law problems they were, so you don't even know if this is a Boyle's law or a Charles's law or a Avogadro or combined gas law or ideal gas law. And just by looking at the problem, you can immediately knock out all those dudes' laws, because this problem doesn't tell you that anything's changed. It doesn't say that the volume's changed, pressure's changed, or temperature changed. It gives you 3 out of the 4 variables. Remember, your 4 variables are volume, temperature, pressure, number of moles. It gives you 3 of them, and it asks you to solve for 1. So what equation do you know includes those 4 variables? The ideal gas law. PV is equal to nRT. And R will always be provided for you. R is 0.0821 liters times atmosphere per mole Kelvin. So, you know pressure, volume, the gas constant, and temperature, and you're trying to solve for number of moles. Algebra says if you have one equation and one unknown, you can solve for it. So let's solve for it. Pressure is equal to 2.31 atmosphere. Volume is equal to 20.0 liters. Number of moles, we don't know. That's what we're trying to solve. R is equal to 0.0821 liters atmosphere per mole Kelvin. T is 35 degrees Celsius. Remember, it needs to be in Kelvin. So 35 plus 273 is 308 Kelvin. Okay, so let's take these values and plug them into the equation. Or let's rewrite the equation first. We want to solve for n, but it's being multiplied by r and t. So how do we get rid of it? Throw to the other side. So n is equal to PV divided by RT. Very good. So let's just rewrite it. N is going to be equal to all that business there. So we have our pressure, volume, R, temperature. Okay. We can just go ahead and type that into our calculator, and we get 1.83 moles. And that's your answer. All right, so that's how you would do it. That's the kind of ideal gas law problem you can expect from me. There's another kind of problem where you can incorporate ideal gas law, but yeah, anytime we're not doing a before and after change scenario, typically we're looking at ideal gas law kind of problems until we learn the next gas laws. So let's see, so far we've done Boyle's law, which is P1 V1 equals P2 V2. We've done Charles's law, which is V1 over T1 equals V2 over T2. We've done Guy-Lussac's law, which is P1 over T1 equals P2 over T2. We've done Avogadro's law, which is V1 over N1 equals V2 over N2. We've combined them all to get P1 V1 over T1. And then we've come up with the ideal gas law, which is P equals nRT. So that is a total of 1, 2, 3, 4, 5, 6. There are 2 more gas laws to go over, and they are Dalton's law of partial pressures and Graham's law. But I'm kind of tired, so I'm going to go ahead and just make that another lecture. So enjoy.